Section 4.4, Exponential and Logarithmic Equations. We're going to be solving exponential equations by expressing each side as a power of the same base. First, we'll rewrite each equation with the same base. Then, if the bases are equal, the exponents must be equal. So we'll set the exponents equal to each other and solve for the variable. In example 1, notice that 5 and 125 can both be written with a base of 5. So we'll begin by rewriting 125 as 5 cubed. Now, since the bases are the same, the exponents must be the same. So we set those exponents equal to each other. Then we solve. We add 6 to both sides. Then we divide both sides by 3. So that's our answer. In example 2, we notice that 8 and 4 can both be rewritten with a base of 2. 8 is 2 cubed and 4 is 2 squared. Then recall that when you raise a power to a power, you multiply exponents. So on the left, we multiply the 3 times the x plus 2, so we get 2 to the 3x plus 6. And on the right side, we'll distribute the 2 to the x minus 3, which gives us 2 to the 2x minus 6. Since the bases are the same, the exponents must be the same, so we set them equal to each other and solve. We notice that we have x's on both sides of the equation, so we'll subtract 2x from both sides. When we subtract 2x on the right, all we have is the minus 6, and when we subtract 2x on the left, we get x plus 6. Next, we subtract 6 from both sides, which gives us x equals negative 12, and that's our answer. Next, we'll use logarithms to solve exponential equations. We'll begin by isolating the exponential expression. Then we'll take the common log if the equation involves base 10. We'll take the natural log if the equation involves any other base. Then we'll simplify using one of these properties. The natural log of b to a power, we can bring the power down in front. The natural log of e to a power just gives us the power. And the common log of 10 to a power just gives us the power. After we do that, we solve for the variable. In example 3, notice that 5 and 134 cannot both be written using the same common base. So therefore, we look at the bases, and since it's not base 10, we'll take the natural log of both sides. We then can slide the x in front, and now we have x times a constant equals a constant. So we can get x by itself by dividing both sides by that constant. So x equals the natural log of 134 divided by the natural log of 5. This is the exact answer. We can also use our calculator to get an approximate value. The solution set is typically looking for the exact answer. In this problem, 10 and 8,000 cannot be written using a common base, so we'll take the log of both sides. Because this involves base 10, we'll take the common log of both sides. So that's the log of 10 to the x equals the log of 8,000. The common log of 10 to a power simply equals that power, so we just get x equals the log of 8,000. That's the exact answer. We can also use our calculator to get an approximate answer. The solution set shows the log of 8,000. In example 5, once again, we have a situation where we cannot write both sides with a common base, so we'll take the log of both sides. It does not involve base 10, so we'll take the natural log of both sides. Once we do that, we can slide the exponents down in front, and then we need to distribute. So we'll distribute the natural log of 3 to the 2x, giving us 2x natural log of 3. We then distribute the natural log of 3 to the negative 1, giving us minus natural log of 3. That's going to equal, and then we distribute the natural log of 7 to the x, and we multiply natural log of 7 times the 1. We now need to continue solving by getting the x terms on the same side. 2x natural log of 3 will leave where it is, and we'll transpose the minus natural log of 3 because it's just a constant term. We'll take it to the right side. The x natural log of 7 will transpose, bring it to the left side, so we change its sign. And the natural log of 7 will leave it on the side with the constants. Because x is common to the two terms on the left, we can factor it out. Finally, the parentheses to the right of x contains only constants. So algebraically, this is x times a constant, So we can get x by itself by dividing both sides by that constant. So we get x equals the natural log of 3 plus the natural log of 7 all over 2 natural log 3 minus natural log 7. This can be approximated using your calculator, and the solution set shows the exact answer. Next, we'll use the definition of a logarithm to solve logarithmic equations. The first step is to express the equation in the form log base b of m equals c. We then use the definition of a logarithm to rewrite the equation in exponential form. Remember, the log base b of m equals c is equivalent to the exponential expression b to the c equals m. We can then solve for the variable. For these problems, we have to check the proposed solutions back in the original equation, and we can only include solutions that give us arguments of the log that are greater than 0. Let's take a look at this example. We have log base 2 of x minus 4 equals 3, so we can change forms, giving 2 to the third power equals x minus 4. We then solve this equation. 2 to the third is 8, and we can get x by itself by adding 4 to both sides. Notice that this says 12 equals x. Many times on the last step, if x is on the right, they switch it around and they'll write x on the left side. Now this is only a proposed solution. The 12 has to make our argument positive, so we have to check it. We'll take the 12 and substitute it in for x. The log to the base 2 of 8 is 3. Since 3 equals 3, that's true, so the solution set is 12. In example 7, we'll again solve this by changing from logarithmic form to exponential form. But first we have to isolate the log. It has a coefficient of 4, so we divide both sides by 4. And then, to change form, since this is the natural log, the base is e, so we'll get e to the second power equals the argument of the log. And now we want to solve for x. Since they're multiplying x by 3, we'll divide both sides by 3. Notice that they spin it around on this step as they divide it by 3. We need to check our answer, so we take our proposed solution of e to the second over 3 and we substitute it in for x in our original equation. The 3's cancel, so we get the natural log of e squared is just 2. So 4 times 2 equals 8. That's true. And so the solution set is e squared all over 3. Again, in example 8, we'll solve by taking this from logarithmic form to exponential form. But first we have to use the product rule to change the sum of this log to the log of the product. Now we can change forms. Since this is a common log, the base isn't written, so it's assumed to be 10. So we get 10 to the first power equals the argument. Now we have to solve for x. To do so, we distribute the x, getting x squared minus 3x on the right side. 10 to the first is just 10. This is a quadratic, so we'll get everything to one side. And factor. Remember, after you factor, you set each factor equal to 0, and then solve each of those equations. X minus 5 equals 0 gives us x equals 5. X plus 2 equals 0 gives us x equals negative 2. These are proposed solutions, but we need to check both of these solutions. We'll substitute 5 in for x, and we'll simplify. 5 minus 3 is 2. We can use the product rule, so the sum of the logs is the log of the product, and that gives us the log of 10 equals 1, and that's true. Now we'll check negative 2 by substituting negative 2 into both sides, and we can stop immediately because the first expression is asking us to take the log of negative 2. Since we cannot take the log of negative 2, then the negative 2 does not work. So our solution set only contains the one that works, so the solution set is 5. Next, we're going to use the one-to-one property of logarithms to solve logarithmic equations. We'll begin by expressing the equation in the form log equals log, with both logarithms having the same base. The one-to-one property of logarithms tells us that if the logarithms are equal and their bases are equal, then their arguments need to be equal. So we can set those two arguments equal to each other, and that will give us an equation that we can solve for our variable. Once we get our proposed solutions, we need to make sure to check them in the original equation to make sure that none of our proposed solutions make our arguments of our logarithms negative or 0. In this example, We can rewrite the equation as log equals log by recognizing that the subtraction of the two logs on the right can be condensed using the quotient rule. Once we have log equals log, and the two logs have the same base, they're both natural logs, so base e, then we can rewrite this as the argument of one log equaling the argument of the other. We now need to solve this equation, so we'll multiply both sides by the x plus 1. That will allow the x plus 1's to cancel on the right. So on the right, it just leaves the 7x minus 23. On the left, we'll multiply that out, and then we need to get everything to one side with 0 on the other. So we'll get rid of the 7x by subtracting 7x from both sides, and we'll get rid of the 23 by adding 23 to both sides. That gives us x squared minus 9x plus 20 equals 0. We then factor and set each factor equal to 0. If x minus 5 equals 0, then x equals 5. X minus 4 equals 0 gives us x equals 4. 5 and 4 are our proposed solutions, but we need to check them. To check 5, we substitute it in, and we simplify, and that gives us the natural log of 2 equals the natural log of 2. So that checks. Next, we'll check the 4. We substitute it in and simplify, and we get 0 equals 0, which is also true. So that checks. So our solution set contains both 4 and 5. Now we'll work on an application problem. How long to the nearest tenth of a year will it take $1,000 to grow to $3,600 at 8% annual interest compounded quarterly? Recall our compound interest formula. We substitute in all the values. The $3,600 is the future value. P is the principal, the present value, which is $1,000. The interest rate of R is written as a decimal, so 0.08. And N is the number of compounding periods per year. Since this is compounded quarterly, both occurrences of N will be 4. And T is unknown because that is the number of years. That's what we're trying to solve for. Notice that our variable is in the exponent. That makes this an exponential equation. And to solve that, we want to get the base to the power isolated. So that means that first we can clean up what's inside the parentheses. But now we want to get rid of that 1,000 by dividing both sides by 1,000. We then take the log of both sides. And this allows us to use the power rule to slide the 4t down in front. At this point, we can solve for t. Though this may look complicated, notice that t is the only variable. Everything else shown in this equation is just a constant. So we can get t by itself by dividing by the coefficient of 4 and the coefficient of the natural log of 1.02. So we divide both sides by 4 natural log of 1.02, and they spin it around, but that gives us t equals the natural log of 3.6 divided by 4 natural log of 1.02. We can run that through our calculator, which is approximately 16.2. That means that after approximately 16.2 years, the $1,000 will grow to be worth $3,600. Let's look at another application problem. The percentage of adult height attained by a girl who is X years old can be modeled by this logarithmic function. At what age has a girl attained 97% of her adult height? To solve this equation, we don't know the x to substitute in. We know the f of x value is 97. So now we have to find x. This is a logarithmic equation, so we have to isolate the log. So the first thing we'll do is subtract 62 from both sides, and then we divide both sides by 35. We now can change forms. Because this is a common log, the base is 10, so we get 10 to the first equals the argument of the log, and now we have to solve this equation. By adding 4 to both sides, we get x equals 14. This tells us when a girl is approximately 14, she'll be about 97% of her adult height.